Welcome back to this lecture on algorithm design and randomization. As you recall, we're talking about algorithm design as it pairs with data structures to create programs, as that's a next major topic you might be talking about in your classwork. And there are broad classes of algorithms that we have discussed. The one we're talking about today, randomization, crosscuts sort of all of these in some way. And it can be applied in many situations. So let's just dive right in. I want to go through a number of examples to illustrate more how randomization can be used to beat worst case behavior in algorithms. Let's start with quicksort. We've talked about quicksort and how the basic algorithm is to do the following. First, choose a pivot, which is a value from the array itself, the array A that we've been given, and use that pivot value to split the array into two portions, the left and the right portions, AL and AR. And once we've split the array into two portions, which could be, larger on one side or larger on the other, we recursively quicksort the left portion and recursively quicksort the right portion. The running time of quicksort depends heavily on how well we pick that pivot. If we pick the pivot so that the two portions are evenly sized, then it has a great running time of n log n. But if we do a poor choice, such as picking the first or the last element of the array A, then it's very easy to give the algorithm an input, which is something like an already sorted array, which forces the algorithm to take n squared running time instead of n log n. And you can see this because if you think about an array that's already sorted and so on, if we pick the first value as the pivot for the whole array, we would partition the array into a left portion, which is just the one, and the right portion, which is everything that remains. And then when we recurse on the right portion, we'd pick the 2 as the pivot and partition into just the 2 and everything that follows. And this degrades into n squared worst case behavior, which is much worse than n log n that we want. We can think about this as if an adversary, someone who we were doing battle with, were choosing the input and trying to get our algorithm to behave as badly as possible or as slowly as possible. And so they're trying to give us an input. We design the algorithm and our adversary is giving us an input that takes a long time to solve. And if we choose our pivot based on the first or the last element of A, then it makes it easy for the adversary to give us a bad input that takes n squared time. And we talked about how to fix this. We can randomize quicksort by choosing a random element of A as the pivot. And so the chances are that we're going to pick something that's somewhere not the first or the last value of the array, but somewhere closer to the middle value, the median value. Remember that the best option for us is to pick the median value, but we don't know where that is. So picking one randomly is likely to pick us something closer to the middle than the first or the last. Of course, there is a small probability of still doing something terrible, like picking the worst pivot, the first value or the last value. And the chance, since there are two of them, if there are n values in our array, picking the worst pivot one time is 2 over n. And that's not a game changer. I mean, that doesn't destroy the algorithm if the algorithm picks one bad pivot. The worst case happens when we pick the worst pivot every single time. And what are the chances that we pick the worst pivot every single time? Well, it's not exactly this, but it's upper bounded by this, basically raised to the power of the number of times that we make that worst case decision, which is something like 2 to the n over n factorial. And that 2 to the n looks big, but n factorial is much bigger. And so we've plotted this probability over here. And again, this is an upper bound, and that's for always choosing the worst pivot of the first or the last. The probability that we do that randomly basically goes to 0 as soon as we hit n equals 10, right? This is 0 probability, and we basically get there. So there's basically no chance that you'll always choose the worst case pivot every time, and that's pretty good. But that's the worst case pivot. If you can think about the worst case pivot, it's either the first or the last. In other words, really it's the least or the greatest value. If you think about the second least or the second greatest item, those are also bad, almost equally bad. We could choose those. Without doing a full analysis, we could define sort of good pivots and bad pivots as pivots that come from sort of the outer bands of this sorted array or the middle portion of the sorted array. So we don't have a sorted array, but if we did, and we thought about the sorted array as having three regions, and this is the good, and these two are bad. And we have a third in each of these. So again, this is the sorted array, which we don't have, but you can imagine that if we define good pivots as the ones that, if they were sorted, came from this region in the middle, right? And there's a 1/3 chance of picking a pivot value from that middle third region. So the probability of picking a good pivot is 1/3. The probability of picking a bad pivot is much higher at 2/3. But what's the probability that we would repeatedly pick bad pivots over and over and over again, k times? And why k times? Well, we could define this as all the time for the entire algorithm, but let's just think about, well, we could make a bad decision once, and then twice, and then 3 times, right? At the top level of the recursion, we might pick one bad pivot. That's not the end of the world, but then we have these two subroutines or recursive calls. We might pick bad pivots in those two. So now k equals 3, the bad pivot here, here, and here. What's the chance that we do it k times? Well, the chance that we do it k times in a row is 2/3 to the k, which is a function that's decreasing exponentially, very quickly going to 0 as k increases. So the probability that we're going to get a lot of bad pivots over time is vanishingly small as k grows, and k grows as the size of our array grows. So the probability that we're going to get bad pivots a lot of the time or all the time is very, very, very small. And the upshot here is that the adversary could choose any array. In fact, they might choose an array and we might make some bad decisions on our pivots and we might have a slow runtime. But given that same array again, we would make different random decisions and we might have a better runtime the next time. So the adversary might get lucky sometimes due to our random chance choices, but there's no strategy that the adversary has that can always defeat our random choices and force our algorithm to run slowly. Now, this is not a thorough analysis of this algorithm. A thorough analysis would be nice, but we don't have the time for doing that. It's a bit involved. But we could do it, and if we did it, we would find that the expected running time of randomized quicksort is n log n, which is what we would like. So the average time for any array is expected to be n log n, which is good. Early in the semester, we talked about binary search tree balancing and how we might keep a binary search tree balanced using something like AVL trees or red-black trees or something like that. And I introduced this idea of, well, what if we didn't want to write all the code that balanced the tree? How could we get a somewhat balanced tree using a simpler method? And what I proposed was, what if we use an unbalanced binary search tree? So it could be in any shape. It doesn't try to maintain balance in any way. But we do it by taking the data that we want to insert, if we know upfront all the data we want to insert, and then we shuffle them and insert them in random order. So if we're given the numbers 1 through 10, we might insert them in any randomized shuffled order. And then we ask the question, without explicitly balancing the tree, how balanced did the tree become after we constructed it? And there is a small chance, and ridiculously small chance, that the tree does not branch. In other words, that the tree ends up looking like this, right? Or conversely, it ends up looking like this, right? Both of those, and so on. Or it could be that the tree ended up looking like this, which is equally bad in the sense that it doesn't branch. And all of these go all the way down, right? But in practice, there's such a vanishingly small chance that this happens that it's practically impossible. And I sort of proved this using experimentation. We can, the chance of getting this tree before we move into the experimentation, the chance of getting this tree, of course, is 1 over n factorial, right? And that's a vanishingly small number. And that's the same as the probability of getting this tree and this tree, because we'd have to pick the order and get that lucky to get that order just right to get, in this case, the greatest value in first and then the second greatest value in second, and so on. Well, we did an experiment, and I did 10,000 trials. And in each of those 10,000 trials, I inserted 1,024 values into this unbalanced tree, but in random order. So the deepest tree we could possibly get is one of these non-branching trees, which would have a depth of 1,023. And and that's the worst case. And the best case scenario is that we get a perfectly balanced tree, which has a depth of 10 for this meant for 1,024 items. Well, the experimental results showed us that the deepest tree had a depth of 33. That's not all of the nodes in the tree, that's just the deepest leaf. And the average over all 10,000 trials was 22.16. So the worst case that we ever saw out of all 10,000 trials was 33. The average case was 22.16. And that's much closer, as you'll see, to the best case scenario of 10 than it is to the worst case scenario of 1,023. So randomization really did a good job of sticking much closer to the best possible case than to the worst possible case. Finally, I want to introduce a new topic, primality testing. Primality testing is determining whether or not a number is a composite number or a prime number. And of course, a prime number is one that cannot be divided by anything but 1 and itself, and a composite number is not a prime number. So 3 is a prime number, 7 is a prime number, 9 is not a prime number because 9 can be divided by 3. This is code that would work for determining if a number was prime. It's not good code because, as you can see, it's slow. Given an integer x, we look at different potential factors, which we'll call I. We start at 2, and we go until, essentially, this code is short for, or a different way of saying, I is less than or equal to the square root of x. And if you think about it, you'll know why we can stop at the square root of x. It's just that this does it with integer math, and we increment I. If x mod I is equal to 0, that's another way of saying if x is divisible evenly by I, then we can return false. In other words, this is a composite number because I was a factor of that number. And if we get through this entire loop and we haven't returned false, then we can return true. This works, but it's slow. And the reason it's slow is because if we think about not just the value of x, but the bitwise representation of x, the number of bits in x is essentially n equals log base 2 of x. And if we think about that, then this runs in time essentially 2 to the n, roughly speaking. Okay, so this is an exponential time algorithm in terms of the number of bits of x. And you might say, well, why are we counting the number of bits of x? Well, because if you want to deal with a really large number like 100 digits, right, then this is going to run in 2 to the 100th time. And that's going to be really slow, even though the number itself only has 100 digits in it. It's fairly small to write down, but the running time is going to be ridiculously large. So randomization can save us here if we're willing to be wrong sometimes. Okay, and now this code is not that understandable at first, but what I want to show you is not the inner details of how it works, but to give you an idea for what might be possible. Okay, first of all, you'll notice that this function is called isProbablyPrime, and right there you say, well, why is it probably prime? Well, because as we'll see, there's a chance of that this algorithm makes a mistake. Okay, what does this algorithm do? Well, it exploits something called Fermat's Little theorem to determine if some randomly chosen factor I, and we choose that randomly, uniformly between 2 and x minus 1, okay? We take that and we compute I to the power x minus 1 mod x. So this mod pow is shorthand for I to the power x minus 1, all of that mod x. Okay, that's what that I x minus 1 x means. Now this mod pow is not a function in C++, but we could implement it fairly easily. And it can be implemented to run in linear time, okay, in terms of the number of bits of x. And if that's equal to 1, then we believe that it's a prime number. So for all prime numbers, this value is equal to 1, okay? And if it runs in order n time, then it's exponentially faster than the previous algorithm. Now, one issue that we can face with this algorithm is that it could make mistakes. For example, if we plug in a composite number, then it could tell us that it's a prime number, and that would be wrong, right? So if x is a prime number, this will always tell us the truth that it is a prime number, no matter which random choice we make. And if it's a composite number, it could tell us that it's a prime number, or it could tell us that it's a composite number, depending on which random choice we make, okay? But the probability of making that mistake is less than or equal to 1/2. And the proof is based on Fermat's little theorem. And Fermat's little theorem says that for any prime number, for any prime number we have for a to the p minus 1 mod p is equal to 1 for any prime number p and any number a between 1 and p. Okay, and that's exactly what we're doing here. We're choosing a number between 2 and x minus 1. And then if I to the x minus 1 mod x is equal to 1, then Fermat's little theorem tells us that conforms with prime numbers. All prime numbers behave that way. Composite numbers are not always equal to 1, though sometimes they are. But it turns out that half the time, a composite number will return a non-1 number. In fact, most half the time, will it return 1 and lie. There are some complications due to something called Carmichael numbers. That's outside the scope, but they can be resolved very easily, and the algorithm still runs quickly, okay? Now, a 50% chance of error. Remember, if it's prime number, it always tells us the truth. If it's a composite number, it can lie to us up to half the time. That sounds bad, but if you run it again and make a different choice, then those probabilities multiply together. So not half probability and half probability, but 1/4 probability. So that if you run it k times, then the probability of getting k errors is 1/2 to the power k. And remember that if this algorithm ever tells us that it's composite, we know it's composite because Fermat's little theorem tells us that's the case. We have found a factor we have found proof that the number x has a factor. So what if you ran this 100 times? Then you'd have the probability of making a mistake, if it was composite, of 1/2 to the 100. And could you live with that probability? It's much more likely that you would get a bit error due to a cosmic ray coming and hitting the memory on your computer. So it's a very, very low probability of error. Okay, so it's not always correct, but it's very likely to be if we run it multiple times. With this example, we've actually sort of introduced the fact that there are two different categories of randomized algorithms. And these two categories are what are called Las Vegas algorithms and Monte Carlo algorithms. And these are just names that are applied. What they mean are Las Vegas algorithms always give the correct answer. They make random decisions, but they always give the correct answer. So for example, randomized quicksort will always give you a correctly sorted array. It's just that the running time can vary depending on which random choices we make. A Monte Carlo algorithm can give incorrect answers on occasion, depending again on the random choices, such as this randomized primality testing algorithm. We can sort of blend the two. We can make Monte Carlo algorithms be more like a Las Vegas algorithm by running them multiple times to drive that probability of error much, much, much lower, getting closer and closer to 0, and in essence, always giving us the correct answer, or with some very negligible probability of being incorrect. I want to summarize it with this. Randomness, making random decisions in algorithms, can be a good strategy to avoid worst case behavior, because if we think about an adversary trying to construct an input that forces our algorithm to behave badly, it's much harder to do when we make random decisions. We can make algorithms that make random decisions and give incorrect answers sometimes, or give approximations to optimal answers, but we can sometimes, using math often, bound the chance that we are incorrect or bound the error on our approximation answer. So that's very high level idea of what randomized algorithms are all about. You can study the entire topic again in much more detail, but we'll leave it there. So I hope you've enjoyed this, this dip into randomized algorithms.